Welcome to the Explainer. Today, we're diving into a feature that's kind of hiding in plain sight within NumPy. It's a tiny detail that can have a huge impact, literally supercharging your data analysis by making your code way leaner and faster. Come on, you've been there, right? You're running some analysis, maybe on a pretty big data set, and you're just staring at the screen as everything just grinds to a halt. You check your algorithms, you hunt for slow loops, but you just can't pinpoint the bottleneck. Well, what if I told you the slowdown might not be in your logic at all? It could be coming from the very foundation of your data structures, specifically from the default settings that NumPy automatically chooses for you every time you create an array. All right, Section 1, NumPy's hidden memory problem. So where does this whole issue even come from? Well, it all starts with the basic difference between a regular Python list and a NumPy array. Okay, so we all kind of get the deal here. A Python list is super flexible. It can hold anything, but that flexibility costs you in performance. NumPy's superpower, on the other hand, is its rigid structure. It demands a single data type for every single element, and that's what makes it so incredibly fast. But here's the catch, the part we almost always overlook. The choice of that single data type is exactly where this hidden performance trap is waiting for us. So how do we actually get control over this? We need to get under the hood a little and understand the DNA of a NumPy array. And that brings us to a really simple but incredibly powerful concept, the data type, or as NumPy calls it, the D-type. The D-type is basically NumPy's instruction manual. It's a little tag that tells it, hey, see this big chunk of memory? I want you to interpret it as a bunch of 64-bit integers, or maybe treat these bytes as 32-bit floating point numbers. And the best part is, you can easily check this on any of your arrays just by calling the .dtype attribute. And NumPy gives you a whole menu of these D-types to pick from. You've got your integers, your floats, booleans, you name it. Now the really interesting part here are those numbers, the 32 and the 64. These tell you how many bits of memory are used to store each value. A 64-bit integer takes up literally twice the memory of a 32-bit one. And guess which one NumPy often picks by default? Yep, the bigger 64-bit version. This is where we take the wheel. Just because NumPy makes a default choice that's a bit of a memory hog for what we need, it doesn't mean we're stuck with it. We have a simple, powerful tool to change it. Meet the as-type method. It's super straightforward. As you can see here, we start with a default array of floats, which NumPy labels as float64. By simply calling .asType np.int32 on it, we create a brand new array. Now the decimals get dropped, sure, but way more importantly, the D-type is converted to the much more memory-efficient int32. So you might be wondering, why bother with this extra line of code? Well, this is where it all pays off. Let's look at the concrete, measurable benefits of making this one simple change.
Let's imagine we've got a big array of numbers, and all of them could easily fit inside the range of a 32-bit integer. By default, NumPy might store it as int64. So we're going to create a second version where we explicitly cast it down to int32. It's the exact same data, just a different D-type.
And this chart just says it all, doesn't it? The default int64 version takes up 24 bytes of memory. But look at our optimized int32 version. It's just 12 bytes. We've cut the size in half. The visual proof is right there.
So the bottom line is this. By consciously choosing the smaller, but still appropriate data type, we instantly cut our memory usage in half, 50%. Now scale that up from a tiny 3-element array to one with 3 million elements. We're no longer talking about saving a few bytes, we're talking about saving megabytes, maybe even gigabytes of RAM. And less memory usage also means faster processing.
Okay, but what about data that isn't just simple numbers? Let's quickly go over a few special types that come with their own set of rules.
For text, you can use a string D-type like U10, which fixes space for Unicode strings up to 10 characters long. But just a heads up, NumPy is built for number crunching. If you're doing a ton of heavy string manipulation, you might actually be better off just using a standard Python list. And of course, it also handles complex numbers with its own dedicated D-types.
And then there's the object data type. Think of this as your escape hatch. It allows a NumPy array to basically act like a Python list again, holding all sorts of different things. But it is absolutely a double-edged sword. Using it gives you flexibility, but you completely throw away all the performance benefits that make NumPy so great. You lose memory efficiency and, most importantly, you disable NumPy's blazing fast vectorized operations. You should only use it when you absolutely have to. So let's bring this all together.
what does this actually mean for you and the code you're going to write every day?
It really boils down to 3 key things. First, memory. You use way less RAM by picking the smallest data type that's appropriate for your data. Second, speed. Smaller data means faster processing and faster calculations. And third, precision. You are now making a conscious choice to either preserve decimals with floats or save space with integers.
This isn't just some abstract technical detail. This is a new superpower for your coding toolkit. Instead of just passively accepting NumPy's defaults, you can now actively look at your data's needs and make an informed choice. You can build code that is leaner, faster, and frankly, more professional.
So the next time you're loading data or creating an array, just take a second and ask yourself, what's the D-type here? Could a smaller one work? The answer to that question could unlock a level of performance you didn't even know you were missing. What hidden optimizations are waiting to be found in your code?